And also, if you have any, maybe you find a problem with the schedule, let me know at least next Monday, or okay, at least next Monday. Okay, I think we can start the course. We're still on chapter 7. Okay, chapter 7. So chapter 7, let me write the content. The first will be the techniques of integration. And the second part is improper integral. And the last part will be the approximations. But I think for approximations, we will see if we can make it or not. If no, then I will skip the approximation. And we already done with the technique of integrations. We have parts, integral by parts, the trig integrals, and trig sub. And the last is partial fractions. Now we are going to learn the partial fractions. Okay. So this will be our discussion today, partial fractions. So first, let's consider let's consider the the fractions that I show you. Okay, so 2 over x minus 1 minus 1 over x plus 2. Okay? You can solve it and make it into one big fractions. And you can solve it and you get x plus 5 and you get x squared plus x minus 2. Okay. So we can write the 2 over x minus 1 minus 1 over x plus 2. It's become x plus 5 over x squared plus x minus 2. Okay. What partial fractions means is this arrow. Okay. So this is what we call the partial fractions. Okay. So okay. So if you see any fractions, okay, like this x plus 5 over x squared plus x minus 2, okay. If you see that form, and maybe integral in integral form. One way to deal with the problem is to separate, okay? To separate the fractions, become separated functions, okay? Become 2 over x minus 1 and 1 over x plus 2. And then you can integrate each fractions in easily, okay? So that's the idea of partial fractions, okay? So I can rewrite this, okay? If you are asking to integrate this, and yes. And you can write this as 2 ln x minus 1 and then minus ln x plus 2 and plus c. Okay, that's the basic idea for partial fractions. So what you need is you need to think the big fraction as a simple fractions. Okay. And most of the cases, if you see any rational functions and you see the polynomial, okay, you see the polynomial degree that you can think, like, for example, this part at the bottom, you can factorize, right? X squared plus x minus 2, you can factorize these terms, and you can actually make it into two terms, two fractions, and then each fraction you can integrate easily. Okay? That's one thing. And also, if you have like maybe not as easy as this one, but still you can factorize and maybe make it um, more separated. You can also use this idea. Okay? Let me just write the the definitions. Okay? So if you have a functions that is rational, okay, let's say the top one is p and the bottom one is q. Okay, p is for polynomial. Q is the quotient. Okay, the denominator functions. Let's say we have p. Okay, we have px. Let's define this as a polynomial function, and then plus, and then plus. Let's say the very end is a1x plus an. That's polynomial. And if, okay, degree of p is n, okay, and if degree p and degree p is at least equal with degree of q, then you can write the functions of x. Let me write p over q is equal a new functions s plus r over q, and r is the remainder. Remainder. So remainder is if you cannot factorize the polynomial completely, the functions that's left in those functions is called remainder. Okay. And for those of you just come, okay, final exam. Please take some notes for the schedule. Okay. Okay. Now let me give you some example. Okay, maybe on here. So to get these results, you can use the polynomial long division. Now we have these functions x cubed plus x over x minus 1. Okay. I think it's simple enough. You can find it, use the polynomial long division. Or if you have just linear functions like this one, you can check with the synthetic divisions. So you will have, let me write the whole functions. So let me write this as x squared plus x plus 2 plus 2 over x minus 1. And then close bracket and dx. And now I can integrate separately. Okay. So 1 over 3 x cubed plus and plus 2 ln x. 2 ln x minus 1 and then plus c. Okay. I think the long division and the syntactic division is quite useful for solving the partial fraction. So if you need to review, I'm suggesting to review the polynomial. Okay, if you don't remember how, review the polynomial parts and especially the syntactic divisions, because I think it's really helpful to, if for example, okay, you want to know whether the some functions, some polynomial function is factorizable or not. Okay, you can find the factors, like for example, trying easy number like 1 or maybe -1 or maybe 0 or maybe 2, and then check whether it's having 0 here or not. If this number becomes 0, then that number becomes the factor, the factor of the function. Okay? And if it is having any left number like 2 here, the 2 become the r, the remainder, okay, the remainder. Okay. So I hope you remember the polynomial parts. Okay, let me continue. At least in our cases to find the integrations, at least we need to think. Okay, we need to think at least four cases. Okay, 4 cases. Let me write in the new page. So you write the functions p and q. So let me write if qx is factorable, then we need to factor it. And then express proper rational function as a sum of partial fractionals of the form A or okay. So at least uh, you will have, I think in this chapter in the partial fractions, at least the denominator will be linear functions or a quadratic, okay, quadratic function. And the top equation will be the left part is a constant a, or it's a linear equation. Okay. Now we go to the first case. Okay, the first case, qx is a product of distinct linear factors. So meaning, okay, the q will be different. Okay, will be different. Okay. For example, okay, let me just give you illustration. So qx, let's say a1x plus b1, and then a2x plus b2, and then until some n. And a1 is not equal a2, is not equal a3, and so forth. Okay? Or I will write this: no factor is repeated. So you will have a nice equations, but different in the denominator. So you will have this form. This is actually what we did in the previous section. So every terms in the bottom is not a repeated factor. Okay, meaning it's different number. A1 is not equal A2 and not equal A3 and so forth. Different factors. Okay. Let me give you this example. Okay, this is the example. So whenever you find rational functions with like having a huge number like this one, uh, I think the only feasible method that really nicely done is using a partial fraction. Okay. First, what you need to think is the denominator, okay? the cube. Think this first thing whether it can be factorized or not. That's the first one. And if you can factorize, you need to factorize and make it into at least several uh, several fractions. Depends on the factors. I think the factors is having cube, right? At least three. Okay, at least three. At least 1, 2, 3. Okay. And if the notations like the integrals and the dx is troubling you, you can just ignore the integration first and just separate the functions first and later integrate it. Okay, I believe it's much more simple that way. So I'm writing the factorized function. And the bottom one become x, and then 2x squared plus 3x minus 2. And I think this can be factorized, right? 2x minus 1, x plus 2. Uh, do you still have problem to factorize this kind of quadratic function? I mean, you need several minutes, or how fast you can factorize. Uh, Let me give you some uh, some suggestions. Okay. So write down the 2x squared plus 3x minus 2. Write down the table. Okay. And concentrate on the left and right. Okay. This is I'm usually using this method to so if you can do factorizations in your mind and faster, I think that will be better. But sometimes if you still have a problem, like you need more time, you can draw a table and put variables here that when you multiply the left part, you will get 2x squared. And write down here, when you multiply this 2, it will be negative 2. Okay. So let me write this. I believe only 2x and x, right? The only possible real number that can having 2x squared. Okay. And then negative 2, you have 1, negative 2, negative 1, positive 2, right? And you can just trial and error. And when you are getting the correct answer, you can check and multiply, cross multiply, whether it's 3x or not. If not, then it's different. Or maybe you can check the other variations. Okay? But I think because it's only like 2 and 2, it's just 2 and 1. The factor is that can be happening. Then you can write this maybe 2 and -1. It's not correct, right? Then you can check the other one. Maybe what? Maybe -1, 2. Okay, now it's correct, right? So 4 cross multiply 4 minus 1 become 3. Okay. This is, I believe, is helping you getting faster, especially if you have, if you're nervous, when you are doing the exam, you can just draw a table and then cross multiply. Okay. So I can write this and make it, let's say, I'm separating into 3 parts. The first part is x, the second part is 2x minus 1, and this third part is x plus 2. And how we are writing the constant here, you can write with any variables you want, but we don't know now, right? We need to evaluate. So write the notations for the constant, just a, b, and c. Okay, that's what we are looking for. Okay. Now we are going to reverse. We are going to reverse this process and finding the a, b, c, and equaling them with the x squared plus 2x minus 1. Okay. So it's like you are making a new equations from from a over x plus b over 2x minus 1 plus c over x plus 2. So you're multiplying this, the x, 2x minus 1, x plus 2, divide by the whole thing, and divide by the x, and then multiply by a. So we can write the equations. So a will be multiplied with the 2x minus 1 and x plus 2 plus b, let's say x and x plus 2, and c, cx 2x minus 1. And this should be equal to the x squared. Let me write equal x squared plus 2x minus 1. Okay. And then we need to solve this long equations here. We are equaling the a, b, c, each of them with the each groups, okay? X squared, x, and the constant. Okay. Let me write here 2x squared minus plus. So writing all plus 3ax minus 2a is equal to x squared. Okay. Now we are grouping based on the x squared is 2a plus b and plus 2c. And plus the x is 3a plus 2b minus c. And the only constant is negative 2a. So it should be equaling to 0. Okay. Now we can write 2a plus b plus 2c is 1. Okay. The x squared is 1. And 3a plus 2b minus c is 2. And then 2a is 1. So a is half. At least we now getting a. Now we can solve the linear equations. You can, I believe you have your preference. Okay? You can use the substitutions, eliminations, anything that can solve the linear equations. Okay, let me solve with the. I will multiply this by 2, and then I will plus this. So I will cancel the c. So it's 5, 2 plus 6 is 8a. And a is half, so 4. So 5b is 1. So b is 1 over 5. And substituting all to the equations, you get 1 plus 1 over 5 plus 2c is 1. So 2c, or let's just write the c, is 1 over 10. And based on our results, we can substitute a, b, c into the equation. It will be half 1 over x, and then plus 1 over 5, 2x minus 1, and plus 1 over 10, x plus 2. Oh, I think this should be minus, right? So this minus. Okay. Now, if you are integrating this, you're integrating it, get the x, integrating then the x. Then we'll write the result is half ln x plus 5 half, I think it's becoming 10. And then minus 1 over 10. Plus C if you want. Okay. So the important thing in the partial fractions is this part actually. This looking the ABC parts. But if you get A, B, C, don't forget to put back to the equations and integrate. Okay? Integrate, okay? Because it's not finished yet. You need to find the integrations. Okay? You need to find the integral. Okay? Okay, any questions? Okay, this is the case 1 in which the denominator will be having a different factor. Now, case 2, let me move to the next slide. So Qx is a product of linear factors. So we can write this. So you have the same factors, but repeated. So if you have maybe x squared minus x plus 1, maybe x squared, x minus 1 cubed. What you need to write is you need to write the, for example, or let me give you the logic. Okay. So first, let's think this as two separable functions. You have the functions, the fractions in which you have the x squared and you have the x minus 1 and then the cube. Okay. The x squared is it's having the linear. Okay. So it will be having ax plus b. And the cube, the top one will having cx squared plus dx plus e. Right? Now we can write this become x squared plus x minus 1 plus x minus 1 squared plus x minus 1 cubed. And nicely, we will have a, b, c, d, and e. Okay. So you see the logic from x squared and x minus 1 cubed. Maybe we see the left part first. Okay. Ax plus b over x squared. Okay. If you separate ax over x squared plus b over x squared, you will see that x will cancel and it will becoming this part, right? And also the same thing is happening in here. So whenever you have any linear factors that repeated, you can nicely having a constant, a constant, a constant, and all the fractions. Okay? And if you need to integrate each of them, it will be really nice integrations. Okay. Let me give you another example. But maybe the example, you can do it by your own. I will move to other problem first. So okay. So to solve this, okay, I have a power 4 and 3. So at least 4 is obvious, it is greater than the cube. Then you can divide first by long division. And then after that, the denominator, you need to find the factors. You need to find, you can factorize or not, the bottom one. Okay. So first we can divide this. We'll write here, or let me write this, let me write just the result of the form. Okay, so x plus 1, it will be x plus 1, okay, plus 4x. But you need to try to divide by yourself, okay? And then the bottom part, we need to factorize this, okay? So qx is x cubed. And how to know whether it can be factorized? You can try 1 or -1, the easy number. Maybe you can try 1 first. 1 minus 1, 0. It's 0, right? So at least 1 is the factor. You can see 1 is factor. And because 1 is factor, I can use the syntactic divisions from polynomial to find the other factors. Wait, it's 0, sorry. -1, -1, 0. Okay, so it is 0. So meaning the 1 is factor, and we can write the qx as x minus 1, and then x squared minus 1. Okay, and then we can solve this, become, and we will have x minus 1 squared and then x plus 1. Okay. Now we can use this to change to change this 4x. Okay. So let me write the x plus 1 plus 4x over x minus 1 squared and then x plus 1. And then we can compute this part first. Okay, we can compute this part first. So 4x and we can have nice fractions. And getting A, B, C. And then to get the A, B, C, it's the same process as we did previously. So I leave that to you. So after you get A, B, C, you plug in the number A, B, C. you integrate, and don't forget we still have the x plus 1 to be integrated. Okay, so you need to integrate x plus 1 and then the whole thing with ABC here. Okay, and that will be the final answer. Okay, and don't forget to plus the constant at the very end. Okay, so whenever you see any linear functions and then maybe it's having cube, maybe squared, maybe 4, you can make it like x minus 1, x minus 1 squared, and if it's cubed, then x minus 1 cubed. Okay. Okay. Now I will move to the next category. The third case and fourth case, I will combine both together. So 3 and 4 will be having irreducible factors. So if qx is having ax squared plus bx plus c, okay. If b squared minus 4ac is less than 0, then this is we call the irreducible factors. So we need to write ax plus b and then the whole quadratic functions. Let's say maybe k. And it can be repeated. Okay. For example, ax. Oh, let me write this is just the quadratic functions first. Okay. And the other one will be with the repetitions. So a1x plus b let's say kx plus bk. Okay, you can write this. So it can be repeated. And let me give you an idea to how to solve. Okay. If you have x over x minus 2, x squared plus 1, and x squared plus 4. Okay. Or let me change this. Maybe squared. Okay. So you can write down x minus 2, and then you will have x squared plus 1, and then plus x squared plus 1, and then squared. Okay. And this part will be bx plus c and dx plus e. Okay. So whenever you find the quadratic functions like the irreducible factors, you need to write the linear equations on top of them. Okay. Now, okay, if you see bx over x squared plus 1, you can use substitutions probably because it's only a constant, right? And it's x squared, you can have 2x and then cancel the x. But how about the, or let me write down the, so you can have bx over x squared plus 1, in which you can integrate easily, right, with substitution method. But the other one, you will have integration of x squared plus 1 dx. And how to solve this part? What's the integration of a constant and then x squared plus 1? Using what? I heard noise, but who? Yeah. So we can use the tangent inverse, right? Arctangent. Okay. So we can use the tangent inverse. Okay. How about if I have now it's not 1, it's 4. It's 4. It's still using the tangent inverse, but you need to write more explanations. It's still using tangent inverse. Any idea? No. Okay. I think in integrations, like I said in the previous class, it's more difficult than derivative because you need to think backward and you need to, at least you know the derivative first, right? So the idea, whenever you forget any formula, okay. I think in your textbook there are some, like in these chapters, like they're like making a box and then using some formula like sine inverse, tangent inverse, blah blah blah. But I think it's not too necessary. What you need to do is you need to keep reminding you need to keep remembering just the derivatives part. Okay? For example, okay, let's start with the tangent inverse, d dx. Okay, this is nicely, you will get this, right? But what will happen if you have the tangent inverse and then 2x? You will get the 1 plus 1 over 1 plus and then 1. Right? And then multiply with the chain rule. Okay? Got it? Got it? Okay. Now, what if I'm divide the x by 2, x over 2? It will be 1 over 1 plus, let's write x squared over 4. Okay? And then we need to multiply with half. This part I can simplify, right? I can simplify and make it 4 x squared plus 4. I need to multiply by half, right? So I can write, let's say x squared plus, let's say any constant a, real number, is equal 1 over a, and then tangent inverse x over a. I'm not suggesting to remembering this. Okay, what I'm suggesting is the idea. Okay, whenever you are keeps forgetting, remembering this, and eventually you will remember this. Okay, so keep reminding the basic idea for integration is from the basic derivatives. Okay, so whenever you forget, or maybe in the exam you find the answers, the integrations, and if you still have time, and you can still derive the equations, you can derive that. And if it's going back to the original equation, then that is correct. But if not, then maybe something is wrong. Okay, something is wrong. Okay. Okay, this I think in partial fractions, especially in these irreducible factors, usually you will get the tangent inverse. Tangent inverse. And the other, okay, so that's one part. And the other part is actually the same thing as the linear factors. You can have the quadratic functions repeated, okay? But it's also the same, you just add ax plus b at the top equations. Okay? So whenever you have maybe 1 plus x squared and then squared, so you have 1 plus x squared here, and then 1 plus x squared and then squared here. Okay? So I hope this case is similar with the linear factors. Okay? So I think for partial fractions, I can stop here and finish. And maybe if we still have some exercise, I can show you tomorrow. And also tomorrow, I'm planning to have improper integral and maybe some practice, And also next Monday, we have quiz. Okay, because we don't really have much time. So 15 will be final exam. And before that, we will still having 1 or 2 discussions, and that will be mostly the last chapters. The last chapters, I will focus on just two sections, the arc length and the surface area. And I think the textbooks have a lot of definitions, but I think I can just go try to simplify the definition for you. Okay. So this is the final exam, and okay, now I can give you the results for your quiz. The average for this class is, I think, quite high. It's around 69. 69 average, the quiz, last quiz.